Hey, welcome, you little crazy kids. We are going to have a brief, yet informative tutorial. What is meant when we say strong versus weak acids, which may be different, probably is different than what you would intuitively think when we say a strong versus weak acid. Okay? So to get into the nitty-gritty really quickly, we're going to talk about dissociation. Especially, right? So again, when we say dissociation, we're talking about an ionic solid that dissolves into water and separates into ions, creating what's called an electrolyte. So let's talk about this. So first of all, I want to dispel what might be a myth that you were thinking, is that the term strong acid does not mean highly corrosive. So when we think strong acid in just general terms, right, the first thing you probably think about is something that's going to eat through a table, or if it gets on your skin, it's going to melt a hole through your hand or something like that. Okay? The term strong acid does not mean that it is a highly corrosive material. Now, a strong acid might actually be highly corrosive, but a strong acid might also not be highly corrosive. And likewise with the weak acid. Okay, so we need to separate the term strong acid from this idea of like something that's going to melt holes through things, or okay. So what a strong acid actually means is it readily donates that hydrogen ion. So when we defined acids earlier, right? Whether it's the Arrhenius definition or the Bronsted-Lowry definition, an acid is always a substance that's donating the hydrogen to another material. Okay, and so a strong acid is something that easily donates that hydrogen. There's no excess or extra energy required to get that process to occur. Strong acid easily and readily donates a proton, which means it would do what we call full dissociation, right? Fully dissociates in water, and therefore creating a strong electrolyte. By the way, the term electrolyte is just simply referring to something that dissolves into water to form ions. Okay? So for example, sodium chloride, which is not an acid, by the way, creates sodium ions and chlorine ions. So something that dissociates into water is an electrolyte. So a solid, it dissociates in water to form ions, is an electrolyte. And the reason it's called an electrolyte is that it allows water to carry an electric current, by the way, right? So salts are electrolytes, okay? And those of you who drink like Gatorade or Powerade, right, those sports drinks, right, part of their appeal, they call them sports drinks, is they replenish at least some of the electrolytes lost through your sweat, right? So you should have noticed at some point that your sweat has a salty taste to it, so that's your body trying to cool itself down, but in the process, a lot of the salts or electrolytes in your body leave with your sweat, and so drinking an electrolyte drink helps to replenish those electrolytes, which helps the little electrical impulses that occur inside your body to make your muscles go and all that stuff. Okay? But anyways, strong acids fully dissociate, which means they readily donate that hydrogen proton, right? And therefore create a strong electrolyte. So the example here, hydrochloric acid, so HCl, technically before we put it into water, right, we would not call it hydrochloric acid, we would call it hydrogen chloride. Okay? Technically not an acid until after it's been dissociated into water. But when we dissociate it into water, right, hydrogen very easily, or hydrogen chloride very easily donates that hydrogen to water to create the hydronium ion, all right? And pretty much 100% of those hydrogen atoms attached to the hydrogen chloride dissociates, okay? Okay? Darn near 100% dissociation of hydrogen chloride. Therefore, when we get full dissociation or nearly full dissociation, we would call it a strong acid. And again, whether or not it is a corrosive material is not determined by this term strong or weak acid. All right, moving forward. Weak acid, again, a reminder, just because we say weak acid does not mean it's non-corrosive. Okay? So in the case of hydrogen fluoride, right, only some, okay, of that hydrogen is actually donated, which means when I put hydrogen fluoride into water, right, some of the hydrogen fluoride molecules will separate into hydrogen and fluoride ions. Okay, again, that would get donated to water to create H3O plus that hydronium ion. Okay, only some of those hydrogens would actually do that. Okay, now again, when I said a weak acid doesn't mean non-corrosive, hydrofluoric acid, HF, is actually highly corrosive. In fact, the frosted glass, or sometimes if you have a bathroom window that you can't see through very easily, glass is normally inert, but things like hydrofluoric acid can actually etch the glass. So frosted glass, or the glass that looks kind of milky and you can't see through it, has often been etched with hydrofluoric acid. So even though hydrofluoric acid is what we would call weak acid, because it only donates some of the hydrogen available, it's still highly corrosive. But again, weak acid does not mean highly corrosive. Strong acid does not mean highly corrosive. The corrosivity is a different property, and it's not implied in the word strong or in the word weak. Okay, a weak acid might be highly corrosive. A weak acid might also be non-corrosive. All right. So again, when we say weak acid, we're talking about only some of the available hydrogen or protons are donated. So we call that partial dissociation, and we create a weak electrolyte. Okay? Now, in terms of notation, how can you tell just by the way the dissociation reaction is written? All right? So if you see a single arrow, that's implying that pretty much all of the available hydrogen gets donated to water to form that hydronium ion. So single arrow represents full or very close to full dissociation. All right? When you see a double arrow, what that implies is that we go with both directions here. And so double arrow means only partial dissociation. So single arrow, strong acid. Double arrow, weak acid. Whoops. Okay? Now, this is qualitative at this point. I can't tell you from the way this is written exactly how many hydrogen or what percentage of the hydrogen fluoride molecules are actually dissociated. Okay? I can just tell you that I know it's not all of them, or so on. So we would call hydrogen fluoride a weak acid, hydrogen chloride or hydrochloric acid a strong acid, and that's simply due to the fact that the HCl molecule splits up fairly easily. Right? To donate that hydrogen to water to form hydronium, the hydrogen fluoride molecule does not split up as easily, right? Only donated some of the H plus to water, right? To form the hydronium ion. Okay? And that is it. You guys have a little practice packet to go along with this info. You guys will probably blaze through that really quickly. Then we'll move on to some stuff about pH, right? And those of you who are in Algebra 2 or have had it, right, we're going to start using logs again. Peace.